And that next lesson that we're doing is all about this first question. We're going to just discuss the asymptotes of this. And then we're going to, hopefully, there's 2 questions that we're going to try to sketch if we can get to them, if we don't run out of time. But then the next lesson, the activity, is all about asymptotes and end behaviors. So you're going to have some time to work through this. It requires some struggle. It's new thinking, and if you feel awkward or if you feel unsure as you're doing it, that's good. That's going to be expected, that it's going to take a bit of time and it's going to seem awkward or complicated or hard maybe even at first. But you work through that like everybody has every other year that calculus happens, and you will get there. Like that's how the whole thing is designed, okay? Once we nail the asymptotes and end behaviors, well, the rest of the sketching is all the same, because it's just taking the derivative, taking the second derivative, doing the chart, and doing all that stuff, and everything else is the same, right? So that's our focus over these next couple of days. There is not a lot of homework. There's only a couple of questions. And that's to give you that time to sort of struggle and work through the asymptotes part of this whole thing, okay? So for this one, we don't need to do any derivatives. We're just going to look at the asymptotes. We'll start with the vertical asymptote. This one's not necessarily hard in this case. What's the vertical asymptote? Thank you very much. It's when the bottom equals 0. So that part is hopefully going to be easy. Oh, darn it. All right, so vertical asymptote is when the denominator equals 0. So when e to the x equals 2. So then how are we going to solve this? Very quickly. Very good. So x equals log base e, or ln of 2. And we'll leave that as exact, but we probably want to know what the approximate value is, right? So I am going to get my calculator up here. When we do asymptotes, one of the things, I would say you can break up these questions into sort of 3 types. 3 separate strategies. It's not quite that definitive, but that's kind of going to be our approach. But there isn't like one way that we're ever going to do it, that's for sure. Even of the 3, every single time is not going to be exactly the same. So what we want to have is several strategies to confirm our suspicions about an asymptote. You might be doing something and say, you know what, I think there's an asymptote here. What can I do to check? And one of the things that we're going to do is we're going to enter values on our calculator. So these questions are probably really good candidates for programming. Whoops. Alpha x. There we go. Programming your calculator in, okay? Anyway, so I'm going to do that, and I'm going to do ln of 2. Just to get the approximate value. Now we're going to do our testing. So remember, for a vertical asymptote, we go just to the left and just to the right. You might be able to do it a little bit by inspection in some cases, if you can tell that e to the x is going to be positive or negative, but subtracting 2, I mean, you can't really necessarily do that in your head, so it's probably going to be kind of tricky. So I'll do 0.68, shift store x, up, equals, and I got a big negative value, so that means the limit as x approaches ln of 2 from the ln of 2 from the left, negative infinity, and I can put 0.7 in, I get positive infinity. So that felt probably fairly natural, kind of normal. Vertical asymptotes are fairly straightforward when you have a denominator and the denominator is 0. Now there's going to be other vertical asymptotes that are not like that, because one of the other things that we always want to be thinking about, and this is going to come up over and over again, but we'll start talking about it now, is what these functions just look like with no transformations and no other stuff going on. We're going to be constantly considering and of course if you change the base, if you have 2 to the x or 3 to the x or 10 to the x, most of the ones that we're going to see will be e to the x and ln of x, but log base 10 of x, log base 2 of x, it's all like got the same shape, general shape to it, right? Same general properties. But we always want to be thinking about those things for sure. So the point here is ln, y equals ln x, has an asymptote. Not because the denominator is equal to 0, but just because that function has an asymptote. Right? So a vertical asymptote. So whenever we're doing ln, which is our third example, we're going to have to consider the fact that there may be an asymptote. And there are other things that can happen as well. So we'll talk about that when we get to it. But we'll have to consider the fact that there might be an asymptote there. But otherwise, if you have something that's got a denominator, then it's where the denominator is equal to 0. Okay, now we're going to look at horizontal asymptote or oblique asymptote. So, this is where there are different types. This type has the e to the x in the denominator. What does e to the x do as x goes to negative infinity? What happens to e to the x? Okay.
Is it just approaching 0?
It's approaching 0, or in other words, getting very, 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 very small. So if where am I here? So this isn't y yet. E to the x goes to 0. So in other words, it approaches yes? So what is it? What is y approaching?
Negative 2.
Negative 2. So see how we sort of, we think about that part, that's the e to the x part, and sometimes there's going to be more than just e to the x, there are going to be more complicated functions. Think about what that's doing, and then think about what's left over. And if this goes to 0, what's left over is fairly clear, and you can write it out if you want. You don't have to, but you can if you want. And say, imagine if this was 0, what would the function equate to? But it's not 0, but it's getting closer and closer to 0. We have to figure out if it's from above or below. So we're going to do another test. What's the number that we usually use for horizontal asymptote testing? 100 and negative 100. But exponential functions can be different. Okay, so if I put negative 100 in for this one, let's see what happens. Why did it do that?
Your calculator can only store so many zeros.
And Exponential functions grow and shrink really fast. E to the negative 100 is like, watch, I could just do that. Shift E to the negative 100. I think I was doing this before. Like, what kind of a number is that? Scientific notation, but it's like 10 to the negative 44. Like, that is an insanely small number. E to the 100. Oh my goodness. Way too big, right? So we're not going to use negative 100 and 100 for exponential functions. 10 is probably going to be good enough. So negative 10, shift store x, up, equals, and that's a negative number, so that's below. Right? It's more negative. It's a bigger 2, but it's negative, so it's below. I'm gonna make a note of that, because this is I think you want to remind yourself of what you're putting into your calculator. You don't normally have to write this down, but I am going to sort of for the lesson. Just so I have a note of that's how we determined that, and we subbed, whoop, I wrote that weird. That's how we determined that it was below. As x goes to positive infinity, what does e to the x go to? In other words, what does the general function do? Where is it going? Come on. Huh? It's increasing. Is it increasing going to some value, or because you can be increasing but approaching like an asymptote?
Is this one going into positive infinity?
It's going to positive infinity, isn't it? Like that graph is just going off, and it's going fast. That's the whole point of exponential growth and exponential functions. So it's going to positive infinity. So, once again, if we take this function, whoops, y equals 4 over e to the x minus 2, this is getting really big. So this is doing what? David?
Getting smaller.
Getting really small, right? We've talked about this a lot. If the denominator is getting big, the overall number is getting small. So in other words, it's going to 0. Now this part I can think about. E, remember, we just said E is getting really big, so pick a value, 1 billion. Minus 2, well, that's positive. So, like, I can tell that it's going to be approaching from above, because it's going to be 4 over some big positive number, so it's positive, and this happens to be 0. That only works because it's 0, and I can tell that it's going to be positive. That being said, I think what the habit that you want to get into is think that through in your head and then check a value anyway to confirm your suspicion. I think it's approaching from above, but I'm going to sub 10 in. And in some cases, you may decide you don't have to. You may, whoa. Did I put 10 in and it did that? Yeah. Crazy. Let's try 5. So very close to 0. I mean, you could tell the other one, if you know anything about scientific notation, you could tell the other one was as well, but from above. So for this one, I did y at, let's say, 5. Generally speaking, the order that I graph, as you all know, is take the derivatives, clean them up, do intercepts and asymptotes before moving on to critical values and PPOIs. That's still the order that I'm going to do things. When you're doing this, it might feel awkward, but you can also know that when you get to your derivative and you find critical values and determine where the turning points are and the intervals of concavity, that will help confirm your suspicions about asymptotes, right? Because if I'm approaching a vertical asymptote from the right or from the left, I'm concave up. So you'll know that it doesn't turn and do something different, because there would have to be a change in concavity, a POI, possibly a turning point or something like that in order for that to happen. So again, by the end, you're going to be able to confirm your suspicions about asymptotes when you do a full graph and you've taken the derivative and second derivative and looked at those aspects as well. So I think that's going to be helpful. But when we're doing this and when we're doing the activity, we are not going to be doing derivatives. So we're just focusing on the asymptotes and trying to do the thinking involving them. But like I said, you're going to be able to confirm it with other things as well. Any questions about that so far? Yeah.
I don't know if we're going over, is this the same for like oblique asymptotes? Like, do you use the same thing for the
Yes. We don't find the oblique asymptotes by dividing or anything like that. It's all by inspection and examining and thinking about the different parts of the function, how they relate to each other, interact with each other, and yeah, exactly. Okay, because there will be oblique asymptotes, there will be horizontal asymptotes. So this is kind of interesting. What's happening here? We have a horizontal asymptote of -2 off to the left, but of 0 off to the right. And this was not something that could happen before, except for in those puzzle graphs that we just made up, right? Where you couldn't have different asymptotes going in different directions. And these graphs do all kinds of things. They have vertical asymptotes, they have horizontal on one side, oblique on the other side, horizontal on one side, and nothing on the other side. It just goes off forever. They can have, sometimes they just stop, and they don't have end behavior on the other side. Like, there's all kinds of things that happen in these. And like mix and match. So it's not quite the same. I think maybe that's part of the challenge is we in an MHF, when we're doing these graphs, we get so used to the fact that, oh, it's an oblique asymptote, so this is how I do it. And there isn't as much of that. Now, that being said, you know, if you're good at making connections and if you do the work and if you are here for the activity on Monday and that kind of thing, you will probably start to get used to the different types. And I mean, there are only so many different types that we cover, and you'll get an idea of oh, this one's probably going to be like that, or this one's probably going to be like that, right? You'll start to pick up on that a little bit. Any other questions? So, turns out we're not doing the derivative, but it turns out that this one doesn't have any turning points or anything like that. So you don't have to sketch it, you can just watch if you want. And I'm just going to do kind of a rough sketch. But it comes down here and goes that way. And it goes this way and that way. Right? Something like that, where this is y equals 2, this is y equals 0, and this is x equals ln 2. This one turns out to be a fairly simple graph. A lot of them are simple in a sense, but most of them will have some kind of turning point and POIs and that kind of thing as well. All right, shall we move on? So we're going to sketch each of the following, and those instructions are pretty lacking, but you know, showing everything that we always show. So this is going to be the full thing. Something that's going to be important. So this one's different. This one is the product of two functions, and two simple functions. The base quadratic and the base e to the x. The last one was e to the x plus stuff, and e to the x was in the denominator. But this one is two functions getting multiplied together. So we're going to have to think about what happens as they get multiplied together. What would be happening, right? So we think about the parts individually. This is what I mean. You look at x squared as what is it, and you look at e to the x as what is it do, like we did in the last example. And then kind of compare them. So what would happen if I multiplied them together? What would happen? Okay, that's how we're going to approach this one. And like I said, doing the derivatives and getting all that together will help us make sense of our choices around asymptotes and such as well. Something that can be good to think about is the domain of the function. Sometimes you might just by inspection be able to tell what it is. Anybody want to have an answer or have a go at what the domain of this function is going to be? The way that I would approach that question is I would ask myself, is there any x value that it can't be? Is there any x value that if I plug into that, literally just put it in, 2 squared times e to the 2, or 3 squared times e to the 3, would any value not work? Can 0 work? 0 is often a odd character. 0 squared, e to the 0 is 1 times 0 squared. Yeah, that's fine. Can negatives work? Can you square a negative? Yes. Can you raise e or any base to a negative? Yes. So this one has a domain. Oops. Of every real number. And that's going to help because it means it has no vertical asymptotes. The vertical asymptote is a place where it doesn't exist. For what purpose would this have a vertical asymptote? There's no denominator. There's nothing else about it. I take two numbers and multiply them together. The other way that I tend to think about this is, again, the graphs themselves. So x squared has a domain where x can be anything. E to the x has a domain that x can be anything, right? E to the x is our exponential curve. You can always multiply two numbers together if they exist. So, right? So, thinking through each of them individually and then how they're interacting. When you're dividing by something, that's different, but when you're multiplying, you're safe. Okay, let's take the derivative. What do we have to think about when we do the derivative here? Product rule. So derivative of the first thing. Go ahead, you can do it yourself. I don't think you have to copy me, but... Once again, pretty easy, right? How are we going to clean this one up?
Factor EX out.
We can factor out an e to the x and an x, good. And we're done. Second derivative. So now I got two product rules. Okay, so go ahead and try this one. factor out an e to the x again. Anybody notice anything kind of interesting about that when they took the derivative? Anything jump out at you?
There were two terms that stayed the same.
Yeah. In other words, the first derivative is in the second derivative. So if you took the derivative again, which is not something that we're going to do, we don't start taking third derivatives of things, at least not in this course, it would like just repeat itself and keep adding on, and then you would, like, it's almost like this weird spirally thing, I don't know. But it's kind of interesting. And that happens a lot with these because e to the x is itself, right? Also, the original function is in each of the derivatives, so it keeps coming up. That's why that process is repeating. Anyway, so that one's done. We've got a quadratic, and we've got an e to the x, and we see e to the x coming up over and over and over again in each of these. But that's done. We'll go on to intercepts. So y-intercept is when x equals 0. That's an easy one. So 0. X-intercept, you don't have to write this down. I'm just doing it because when we see new functions, we always want to go kind of back to fundamentals and back to basics, that kind of thing. So e to the x is never equal to 0, so no solution there. But x equals, or y is equal to 0 when x is equal to 0. Obviously, if you have a y-intercept of 0, you have an x-intercept of 0, so that had to happen. But there you go. Okay, asymptotes. You've got to have a reason for a vertical asymptote. I know I'm repeating myself, but I'm doing that on purpose. You've got to have a reason for a vertical asymptote. Either you have a denominator that's equal to 0, or you have some function that has a vertical asymptote in it. And this one has neither. We already discussed that its domain is every real number. So vertical asymptote, none. Here's where the fun starts. As x goes to negative infinity. The last question was the type where you only had one function in it, really. And so you think about what it's doing, and you kind of think about what's left. How does it impact whatever's left over? This one is two functions. How do they interact? So this is going to be a different strategy or different type of thinking. What does x squared do as x goes to negative infinity? It goes to infinity. Is it fast? Is it slow? What would you say? It's all relative. It goes faster than just a linear function, but not as fast as a degree 3 or degree 4, not as fast as exponential functions, right? Exponential functions grow very fast. So it's all relative, but I would say, what grows even slower? Well, ln grows very slowly only to the right, but grows very slowly to the right. Square root function grows very slowly, also only to the right, but grows very slowly, right? So some like functions grow at different speeds. So x squared is growing to positive infinity. It's going up when it's going to the left. What's e to the x doing? Approaching zero. So I've got something that's getting really, really big going to infinity multiplied by something that's getting really, really, really small like 0. Well, what wins when you multiply 0 by infinity? That is not a discussion we're going to have because it's very complicated and there's actually no full answer to it. It sort of depends. And that is something that you may talk about in university because it is a famous kind of discussion. But anyway, we're not going to get into that. But it's not clear, right? You would think multiplying by infinity would make anything infinity, but you would think multiplying by 0 will make anything 0. So which one do you think is going to win? Which one do you think is going to win? Like, what's your hunch? This is where I think we come up with a hunch. Is e to the x getting smaller faster than x squared is getting larger? Or vice versa? What's your hunch?
Well, I figured that, what's the square one? No, but.
Quadratic?
Yeah, I figured quadratic grows slower than exponential, so if you translate that to it getting smaller, then the e would probably win out.
Okay, good. David, were you putting your hand up? Were you going to have a guess? No? Anybody else want to? So I like Travis's thinking. That's my hunch as well, that e to the x grows and shrinks faster, and it will probably dominate this battle that these two functions are having. One's getting really, really big, and the other's getting really, really small, and they're going to fight. Okay? You're going to multiply them together. But how are we going to settle this to be sure? Well, we're going to test the value. Okay? And the thing about, so I'm going to program this one into my calculator. Alpha x squared times shift e to the x. And I'm going to put negative 10 in. I got a really small number, even just at negative 10. So it looks like e to the x is really winning. Could it do that and then turn up and eventually x squared takes over? That could happen, but that would require a turning point, and this is what I'm talking about. When you go to do your first derivative chart or your second derivative chart, we're going to do second derivative for this one, you'll find out if there's a turning point past negative 10, and if there is, then you're going to have to reevaluate. So you really do have to think about the whole process as a whole when you're going through these. Does that make sense? We could try negative 5. And if you program it in, you're not going to be scared to try a few different values because it doesn't take that long, right? So it's not a bad idea. And what you might do is always try a couple of values and see if you can see a progression. Try 5, try 6, try 7. Okay, yeah, it's getting smaller. Okay, so y is approaching 0. From above or below? Well, we already did our test, so we know it's above. But I also know that x squared is always positive, except for when it's 0. And e to the x is always positive. So our function is going to be always positive, except for where that x-intercept is. Like, I also know that by just thinking about the individual parts of the function. Notice how this is also different from what we were doing before, where we figured out what the horizontal asymptote was and then did the testing. But in this case, we're doing the testing and then sort of concluding what the horizontal asymptote is. We're doing the testing and thinking it through it first. But I'm going to make the statement that I have a horizontal asymptote at y equals 0. What does x squared do as x gets very large? Positive. Going off to the right, it still goes up. It still goes to positive infinity. What does e to the x do as the function goes off to the right? It also goes up. So we've got two things getting very big multiplied together. What's that going to give you? Something very big. So what's happening in this case? Is there an asymptote? Well, it doesn't look like there's a horizontal asymptote.
Yeah, I was just gonna say that, it's like just continuing.
Yeah, and it's not a vertical asymptote either. You got to have a reason for vertical asymptote. Now, it might look like it because it's going to get big fast like exponential graphs do, but nothing. It just has the end behavior of going off to positive infinity. Back like when, at the very first unit of MHF, when we first started addressing end behavior of polynomials, that's the kind of end behavior that they had. They just went off into a quadrant somewhere. And that's what this one's doing. Come all full circle. So no asymptote. Any questions about that? Do you at least get a hint of what this is all about, how this is working? Pulling apart the different parts of the function into individual sort of base functions, thinking about their individual properties, and then how are they relating, whether they're one's being divided by the other, one's being they're being multiplied together, or something like that. And then always, notice we're always checking values on our calculator just to be sure. Okay, I think that's an important part of this process. Okay, you can go away for now. So now we're going to move on to critical values. Y prime. Again, Y prime exists for all values of X. Where does it equal 0? Again, we're going to pull the different parts apart. So this is our cleaned up derivative. Set it equal to 0. So when x equals 0, e to the x equals 0, no solution. And when x equals -2. So we've got two turning points. Okay, second derivative also exists everywhere. E to the x times x squared plus 4x plus 2. What are we going to do for this quadratic? Well, b squared minus 4ac. I'm pretty sure it's not factorable, right? But so it's 8. I can do that in my head. So that works out to, should be -3.41 and -0.59. All right, chart. Oh, let's do the chart first, and then we'll talk about that. Remember the testing that we did? What value did I test? -5? So my two critical values are 0 and -2. So one of them is in this interval and the other one's in this interval. So when it's at -5 and it's really close to 0, it's not turning and going back up. Right? So that helps confirm what we thought about what was happening there. You got to take a minute to think about it, but it does. All right, let's see. I'm going to type in my second derivative here. And I'm going to use a this time. So pick, how about -5? Positive, so concave up. What does that also confirm?
The horizontal asymptote that as x goes to -30, y is approaching 0 from the top.
From above, right? Because if it's approaching an horizontal asymptote from above, it's concave up. Even though it's decreasing, it's concave up. This was one of the fundamental things we talked about when we started exploring concavity. Okay, so again, we thought that it was approaching 0 from above. That confirms it. -2. Is in there. A. So negative. So concave down, and we've got a POI. And the last one works out to be positive, so concave up again, and another POI. Oops, -3.411. -2, which I just did. But in the derivative, not the original one. 5, 9. And 0. 0, that's an intercept. I know that one. Now I'm punching all of these in. I'm going to skip that step because you all know how to do that. I've got it programmed into my calculator, so it's not going to take me too long to do that, right? But I've got them written down, so I'm just going to cheat to save some time so that we can get on to the next one. Whoops. Then we're going to put this all together. So this is a TP, it's in a concave up region, so it's a TP min. Forgot to write this out. POI concave down region, so TP max. POI remember, end behavior is going up there. So if you want to see what this is approximately going to look like, I'll do a quick sketch, but then I'm going to fix it because this isn't going to look very nice. Is I'm coming down like this, turn, up, turn, and go like that. Turning point, POI in here somewhere because this is concave down and this is concave up. Whoops. And this is concave up and this is concave down, so a POI in there somewhere as well. So go ahead and draw it. What's going on here? I think I'm hitting this button. There we go. POI in there somewhere. That looks good. Maybe right about here. Here. A, B, C, and D. Getting cluttered in here. It's interesting how, like, it looks like it has the parabola part when it's near 0, which makes sense because E is about 1 at that point. So you're multiplying by approximately 1, so it's going to look mostly like a parabola, the quadratic part. And then this sort of looks like a quadratic, but you know, the exponential is really what's taking that over because it grows faster. So that would be more like an exponential. And then again, they're battling it out here. The quadratic is winning for a little bit when E is still close to 1, and then E to the x eventually wins over. Cool. Okay, so we'll try to at least get through the asymptote part for this one so that you've seen one of the asymptotes with ln. I don't know that we're not going to be able to sketch the whole thing. We only have 10 minutes left. I might be able to, well, you can finish it yourself, I think. And so we'll maybe, yeah, we can hopefully get the intercepts done as well. And then if you want to finish that and you can look at it online, you can do that. Okay. What's the domain of ln? Greater than 0, right? So it's got an asymptote at 0. It doesn't exist to the left of the vertical axis, of the y-axis. And this only has ln in it. You can't maybe always do this just by inspection, but in this case, our domain is that's what it's going to be, because I can't take the ln of 0 or of a negative number. But all positive numbers are going to work for both parts of this. It's ln and ln squared, not ln of x squared. Make sure that you understand it's not this, right? That's why the brackets are there, to be especially clear. Whoops. Okay, because those are two very different functions. So once again, the domain So power of a function rule for that second part. Second derivative. Now I've done this both ways, using the second line or the third. If you use the third, it's quotient rule. If you use the second line, you also have quotient rule, but it's simpler. And to me, they were both very similar. One wasn't necessarily better than the other. But this is something we've talked a lot about. You got to decide which line you're going to and which one of these you're going to take the derivative of. So negative 1 over x squared. I'm going to do the second line this time. Uh, 2 over x times x. Derivative of bottom is negative 1. Times the top. All over the bottom squared. Whoops. There we go. Nice thing is you still have you have an automatic common denominator here. Oh, we're going to run out of time. I'm going to skip the intercepts and go straight to asymptotes. So whenever you have a ln, like if you have ln in a function with other stuff, it doesn't matter if the other stuff exists to the left of the y-axis, it can't exist because ln doesn't exist. Like it can't, right? So if one part of the function doesn't exist, the whole function doesn't exist. So what we're going to do is we're going to determine the limit as x approaches 0 from the right of y. And I'm going to program this. Nope. Ln of x minus ln of x all squared. Darn, it gave me a math error because it's got 0 programmed in there, I guess. Oh no, it's got a negative programmed in there. So I got to program something else in. So shift, whoops, how about 2? Okay, so I'm going to pick something very close to 0, 0.1. Negative 7. Now I'm going to try another one, and because I've got it programmed, I can do this quickly. Negative 25. Now I'm going to do another one. For this process specifically, I would try a few. Maybe even one more just to be sure. But it looks like it's certainly getting smaller and smaller. Whoops. Negative, getting smaller and smaller and smaller. So it's going to negative infinity. So we've got a vertical asymptote at x equals 0. Notice again, we didn't determine what the vertical asymptote was. If there's one, it's at 0. We know that part because ln has an asymptote at 0. But the other thing that can happen is it just goes usually straight to the origin. And it just stops there, like the square root function. It doesn't exist at 0, but it just goes to the origin. Or there are cases where it will go up. So it could go to positive infinity. It could go to negative infinity like normal log function does. Or it could go to 0. Okay, so you're checking to see which one it is. And once you check a few values like that, you are going to pretty quickly, I think, get a sense of what it's doing. As for the other direction, well, I've got ln x, which is getting bigger, but I'm subtracting ln x all squared. So when I square it, like ln x and ln x are going to be equal. But one of them I'm squaring, so aren't I always going to be subtracting a bigger number than the other one? This is always, as x gets very large, that part's going to be bigger. So the end behavior on the other side, as x goes to positive infinity, we don't have end behavior going to negative infinity because it doesn't go to negative infinity. Y goes to negative infinity. So no horizontal or oblique asymptote, and again, I can plug in, now ln doesn't grow very fast, so let's try something big. Let's see what happens. Not very big, negative 16, but it's negative. You could try something bigger. This one's not going to blow up your calculator because look at how slow that's growing actually. I did 1,000, it's still only negative 40, but it is getting smaller. And again, when you do your derivative chart and you find your turning points, you'll confirm that there are no more turning points over there, so it's getting smaller and it will just keep getting smaller.